Okay, good afternoon. So the title of my talk is Magnetization Dynamics, and I would like to start by thanking Derek Jones for organizing this wonderful event. Unfortunately, I had to miss the first day, which I regret very much. And I had to fly actually today, this morning, so I'm a little bit shaken by all the travel and a delayed flight actually. So excuse me if it's not the best talk. So I'll be talking about magnetization dynamics, and what I mean by this is basically manipulating spins or magnetization by applying different gradient waveforms. And here's an outline of my talk. There are three main sections. I'll first try to motivate why we study the dynamics of magnetization. And then there are two kind of avenues or classes of techniques. One of them involves path integrals. The other one is actually tackling the Bloch-Tori equation. So first, why do we study the dynamics of magnetization? And I will do this by giving examples, mostly on what we've done so far. So it's kind of a flipped organization here. The theory comes later. The results come first. So why do we study magnetization dynamics? And the answer is, I think, clear: to understand how structure affects the signal. And another reason is to assess alternative diffusion encoding strategies and gradient waveforms. And actually, Ivana's talk is a beautiful example of what I mean by this, so I won't elaborate on it much. And so I'll start with a brief example, and this is the anisotropy induced by boundaries. And this is kind of an unusual regime where the voxel size is actually smaller than the pore size. And in this case, I mean, you can kind of envision that the effects of boundaries will have some influence on how the magnetization evolves. And this is due to the fact that the spins near the boundary of the wall is able to diffuse to the left in this diagram, but not towards the right. So there will be kind of a bias, a local character of diffusion. And this is reflected in the magnetization. And in this paper in 2008, we actually showed this effect by essentially acquiring DTI-type data from a macroscopic and large hollow cylinders. We see that there is some anisotropy near the boundaries. These are voxels that do not necessarily contain any part of the wall. It's just water, but they happen to be close to the boundaries, so they feel the existence of the walls, and that's why we call the effect remote anisotropy. And this is actually the real data and the kind of, not the fit, but the expected behavior in the continuous curve here. Obviously, the opposite case of voxel size being larger than the pore size is probably more relevant, especially when you look at biological tissue. And in this case, actually, as suggested by Tori, the double diffusion encoding is a trivial extension of statistical antenna's pulse sequence, which could give you some information on this local anisotropic behavior. And if we look at the magnetization, this is what happens for single diffusion encoding. And I'm looking at a pore which is isotropic, like a cylinder in 2D. And when you apply the first gradient, you essentially induce a phase distribution within the pore, which will look like this. And if you wait for a long time, big delta, then obviously the diffusion phenomenon will even out, will cancel everything, and you are left with a uniform magnetization. And then you apply the second pulse, which will create the same kind of effect. So in effect, you get certain signal. And if you apply the gradient in a different direction, the same phenomenon happens, but in an opposite sense. Okay, and you are left with a different magnetization profile. But what you detect using your scanner is just the sum of or integral of this magnetization over the pore volume. And it doesn't matter whether you have this kind of a profile or this kind of a profile, it will integrate to the same value, right? So when the pore size is small, then you have no way of telling anything about the anisotropy within. So if you have double diffusion encoding with short mixing time, then, and first I consider the case where these two intermediate gradients cancel each other. In this case, you have essentially a single diffusion encoding experiment with a delay time 2 delta, so it won't really matter in the long time regime. And you again get the same kind of attenuation that you get from single PFG acquisitions. If you have the gradients adding up in the center, so if they are oriented in the same direction here, then of course there is an additional attenuation due to the presence of this gradient, which is given by this factor. So that's why the response is very different. And if you look at the history of magnetization, the final state of the magnetization after half of this, or the second pulse is applied, becomes the initial magnetization for the second pair of gradients, right? So that information is being transferred to the second encoding event, and that's how we get some different behavior. And this difference is quite interesting. First of all, if you look at the signal from a closed pore, then the signal you get is just a power spectrum of this pore indicator function, which takes a constant value within the pore space and vanishes outside the pore. If you do a double PFG experiment, because of the phenomenon that I just described, then you have this kind of a response. And of course, this has consequences. This is not necessarily positive or even real. So the signal can be negative. And it can have, it will exhibit these zero crossings, right? The signal actually will go through the horizontal axis and get negative values. And we realize that this can be quite important, especially when you have heterogeneous media, because here, when you have all positive signal, and let's say you have polydisperse material where there is a distribution of pore sizes, then these interesting non-monotonic features will actually smooth out. You'll have a kind of a monotonic decay here. Whereas here, because the signal is positive or it can be negative, there will be some cancellations when you change the pore size. And that's why the zero crossings are actually quite robust. They prevail in polydisperse media. And Noam Shemesh, when he was working with Yoram Cohen in Israel, did a number of experiments, and this is just one of them, where he actually designed a phantom by just literally crushing the microcapillaries and creating kind of a random distribution of pores. And this is the signal response. The red one is the single PFG. As mentioned, it's a very smooth decay. Whereas in the case of double PFG, we have the signal bouncing. Actually, if you look at the sine signal, it actually crosses the horizontal axis and gets negative values. So another important consequence is how double diffusion encoding can characterize different specimens and how it can characterize anisotropy at different length scales. And to illustrate this, I will show 5 different scenarios. One of them involves just one, essentially a test tube filled with water, if you will. And you can have 2 different species, let's say molecules diffusing at different rates, diffusion constants. And you can have some porous materials. The pores can be spherical. They can be elongated but randomly distributed. And finally, they can be elongated and coherently distributed. So, and I will plot the double diffusion encoding signal as a function of the angle between the 2 gradients. In the first 2 cases, when there is no anisotropy, there is no angular change. It's constant. And if you perform the experiment at short mixing times, then you will have this bell-shaped curve in a double diffusion encoding response for spherical pores. And if you have randomly oriented media, then you have this sort of behavior with two dips. It looks essentially like a W pattern. And this is what we realize when we consider essentially just like the Neurite model of Sune Jespersen he talked about earlier. When you have a random distributed one-dimensional pores, we did report this kind of a pattern in this article. But later on, we actually derived that the modulation is described by a cosine tube C function. And the amplitude of this modulation is actually related to the eccentricity of the compartments. So if you have more elongation, it's kind of a sharper modulation. As it gets more isotropic, then it will be flat, more flat. So these are just some interesting findings we had over the years that are related to dynamics of magnetization. Now I will describe it in terms of path integrals, which is quite interesting and powerful. So this is just to illustrate the random movement of a particular spin. Okay, so this is the time axis, and is for different time points. It obviously undergoes different jumps in different directions, so it can assume it's at different places in space. And on the top, I plot the gradient waveform that we apply. It's kind of arbitrary function in this case. And of course, we do the time slicing. So we have we can represent this waveform as a train of impulses, just like this. And if you track just one particle, you'll see that its phase at the end of the pulse sequence will be given by this integral. This is the 3D version of what I illustrate here for 1D. And of course, if you're interested in the overall signal, then you have to consider all trajectories, all possible trajectories. And that's why it's an integral. It's defined by an integral over trajectories. And this is to represent the likelihood of a particular trajectory. And this is the so-called the signal from a single spin following a particular trajectory. So if you integrate over all trajectories, you obtain the signal. So this is a simplistic picture, and it's quite, normally you cannot use it to get analytical results. Actually, you can get it only in the Gaussian regime for very, very small gradients. And there is an exactly solvable model, which is the case of parabolic confinement. Here, we are actually, we are not restricting ourselves to hard walls, but we are saying, okay, instead of hard walls, which would be represented by an infinite well potential, just like that, where the potential is infinite at the walls and it's constant within the pore space, we can consider a softer wall, essentially, where a parabolic potential defines the restriction. And this was actually one of the problems discussed in the original papers. This is a paper from 1965 where they refer to it as diffusion near an attractive center. Of course, we studied it in more detail and in 3D and for arbitrary pulse sequence in this paper. And this is essentially, we do it by defining this potential and introducing this confinement value, which is the force constant of a hypothetical spring divided by the thermal energy. So it has the dimensions of the reciprocal of length squared. Okay. And it basically describes diffusion for particles which are bound by this Hookean spring, essentially. So they are subject to a restoring force when they are away from their equilibrium point. And of course, you can study this problem very easily in higher dimensions. That's one of the strong points of this. And you can, for example, define compartments that are described by 3 different length parameters. And it's easy to do this because this is separable. It's just a quadratic function where we introduced the confinement tensor in this case. And you can get the exact solution using brute force path integral, for example. And the result will look just like the statistical and tenor relationship for the statistical tenor sequence. And instead of the B matrix, now you have this curly A matrix, which contains all the timing parameters, and the diffusion constant is also here. And so if you look at the anisotropy, for example, this is for an axially symmetric shape just like this. As a function of the deviation from the fiber angle, you basically capture the same kind of anisotropy that you get out of diffusion tensor. What sets this apart and makes it relevant for restricted diffusion is when you look at its time dependence. Okay, if you plot the signal versus the pulse separation here, then you will see that the signal will come to a plateau. It will not decay further. If you consider the Gaussian diffusion, it would, of course, decay all the way to 0. So this is consistent with the behavior you get from truly restricted diffusion. For example, here we compare it against the slab geometry. So what if we don't have an explicit solution, which is usually the case? And this is exactly what Ivana mentioned in her talk. Then we have this multiple propagator framework introduced by Callahan based on discretizing the waveform and approximating it by a train of impulses, essentially. This is like almost a numerical implementation of the path integral because it's based on the same idea. And of course, I don't expect you to understand it, but what we have here is essentially the signal, and each of these factors here is just a eigenfunction expansion of the propagator that takes you from one point in time to the next point in time. So once you employ this trick, this substitution, then you can express the signal in terms of the product of some matrices, and these matrices are given by, in this case, integrals over the eigenfunctions of this Laplacian for that particular geometry. So this brings me to the next item on my list, which is the Bloch-Tori equation. So the Bloch-Tori equation basically describes the evolution of magnetization density. It's a little bit like what Schrödinger's equation is in quantum mechanics. And this is the expression. So here we have the diffusion equation here, but we had the additional term here. And this is kind of introducing some complications. This is not a self-adjoint operator, so a lot of the things that we are used to having, the properties, are not applicable. So we have to actually dig in and understand the properties of this operator. And this is actually done to some extent in this paper, so you can find it. So based on this equation, we can actually introduce another matrix formalism. This is not something we did, obviously. It comes from a series of developments by a number of authors, starting 1960s by Robertson, then extended by Barzikan, Axelrod, and Sen, and finally refined by Grebenkov. And Grebenkov called it the multiple correlation function framework. And of course, at the time, I was in Peter Basser's lab, and we were working on these double diffusion encoding measurements. And we had to account for the variations in the orientation of the gradient during the pulse sequence. So we had to generalize this framework. And because everything follows in a straightforward manner from quantum mechanics, we did this generalization simply by invoking, for example, the Wigner-Eckart theorem in 3 dimensions. That's something I learned in grad school. I never thought I would use it in MR, but not in diffusion MR at least. And it turned out to give the answer relatively in a simple way. So, so let's consider only one interval. And because we are actually approximating the gradient waveform by a piecewise constant function, if we consider only one of these intervals, then this term, g of t here, is not time dependent in that interval. And that's why we can use it in this fashion. Qn here is just the integral of the gradient over that interval. And then we can introduce these operators. Here we have a vector operator. So this is a vector of matrices, if you will. So this is just a position operator expressed in the eigenbasis of the Laplacian. And then we basically compute this matrix product. Here, enter these matrices go here, and we have this matrix in the exponent, which is being exponentiated. Then you actually multiply those resulting matrices, and you just look at the very first element, which gives you the signal. So it's a very neat way of writing the results. Then the question is, what is the difference between multiple propagator approach, which is also based on a matrix product I mentioned earlier, and the MCF method? And actually, I also implemented this until I found out about the MCF method. It was working well, but the MCF method is actually quite a bit more efficient if you consider especially pulse field gradient methods. And this has to do with the commutation relations of these matrices. And so you don't have to do any slicing over a constant gradient in the MCF technique. So very few number of multiplications would suffice for pulse field gradient measurements. And it's discussed in this book chapter. So both of these approaches, though, are based on the eigenfunctions of the Laplacian. More recently, we considered the Bloch-Tori operator, which is like the real thing. We don't have to express everything in the eigenfunction of the Laplacian. We can actually consider the operator that involves that particular gradient. And of course, this is an unusual operator. And it's also different for each gradient in your sequence. So you have a different operator at each time point, essentially, which is the drawback, which is a big drawback. But drawing some analogy with quantum mechanics, it's exactly the same thing. Over there, we have obviously the stationary states. Here, we can call these the spiraling states because the eigenstates actually spiral on the transverse plane. The complex part of the eigenvalue will determine the angular frequency, and the real part will determine the radial decay. Okay, sorry. So these are how the eigenvalues look like. So I'll skip through very quickly. And this is, if you wait for a very long time, then you will actually see these eigenstates are localized. This is an explanation of the edge enhancement effect. So we can come up with a new matrix product using this technique. And here we just compare different solutions. The red one is the Laplace-based solution, and the blue one is the Tori-based. As you see, the Tori one starts very bad. The crosses are like the ground truth. This is because the uniform magnetization is not an eigenstate of any of the operator when the gradient is non-zero. But over time, it quickly picks up and actually performs a lot better than the MCF approach if you use very few basis functions. And finally, I want to talk about a very recent approach. This is joint work with Lipang Ning and Carl Friedrich Weston and Yogesh Rathi. Here, I won't describe the detail. Just the essential idea is that we have the space-dependent diffusivity here. And we basically define this diffusivity as having two parts. One of them is like the average diffusivity over the volume, and the other one is a fluctuating part. And this overall object is referred to as the disturbance function. And we can actually write a solution in terms of this disturbance function, which could look like this. And these are just some results on heterogeneous media where Lipang simulated different substrates with different packing densities, etc. And these are how the functional fits to the signal, simulated signal. And this is just showing the ensemble average disturbance. So you can find more about it from this article, which is available online in NeuroImage. So in conclusion, studying magnetization dynamics reveals many interesting phenomena. The confinement tensor model provides explicit expressions and may serve as a realistic representation of diffusion anisotropy. And the Bloch-Tori operation equation is a bit challenging, but it's quite fruitful. So thank you for your attention.